All right, so we are working primarily on chi-squared goodness of fit, and we are going to be also doing some practice with other older problems. Number 1, according to theory, blood types in the general population occur in the following proportions: 46 type O, 46% type O, 40% type A, 10% type B, and 4% type AB. Anthropologists come upon a previously unknown civilization living on a remote island. A random sampling of blood types yields the following counts: 77 type O, 85 type A, 23 type B, and 15 of type AB. Is there sufficient evidence to conclude that the distribution of blood types found among the island population differs from that which occurs in the general population? And then we see about the data proving or giving evidence. So first of all, we can cross off anything that says prove. That is never one of our, that's very rare we prove anything in statistics. That's reserved more for abstract mathematics, geometry, and the like. So again, what is the distribution for our general population? It's at 46%, 40%, 10%, and 4%. My null is that the people on the remote island have the same distribution. My alternate is, maybe they don't. So I still have to check conditions. We have the random condition like we did before. We have a random sample of blood was taken, so we're fine. 10% condition. We must assume the population is at least 2,000, and 200 does not exceed 10%. So we have to assume that, which is probably reasonable. Now, the next thing we have to do is check the large counts condition, which means we have to check expected counts. So we take the given percentage for our general population, change it to a decimal, and multiply it by our sample size, which is 200. Then we get all our expected counts, and they need to be at least 5. So for type O, we have 46%. And if you add these all up, you find out the sample size is 200. So 46% of 200 is 92. If this group were like our general population, we would expect 92 in the sample to have type O. 40% is type A. That's what we would expect, and that would be 80. 40% of 200 is 80. 10% of 200 is 20. And 4% of 200 is 8. This is work by hand, and you should show what I've shown for the calculation. Okay, then we go on to calculating the test statistic, which is this formula, which is on your math chart. Ideally, you need to show work by hand. So this is the most work by hand it's more than you're used to from the z-test and the t-test, etc. So you're going to basically fill in the observed minus the expected. We observed 77 type O, but 46% of 200 is 92, so we expect 92 type O. You subtract those two, square it, and then divide it by the expected, which is 92. Then you have 85 type A, 23 type B, 15 type AB, and then the expected counts for all of those, which you get by multiplying 40% by 200 gives you 80. 10% of 200 gives you 20, and 4% of 200 gives you 8. Once you calculate all that, you get 9.33. And then we can go ahead and say, what's the probability of getting a chi-squared test statistic of 9.33 or higher? For chi-squared, we're always doing to higher, so the chi-squared test statistic is always the lower one. And so the upper one, which I failed to fill in here, is infinity, and our degrees of freedom is 3. How did I get that? I have 4 outputs on the category, and so I just subtract 1 from that, and that gives me 3. So to go ahead and do the chi-squared CDF, you hit second distribution, and it's towards, you can see it right there, it's choice 8. and you have to put your lower and your upper. Our lower chi-squared is 9.33, and then we're going to put upper as infinity. So we're going to go 1 e to the 99, and our degrees of freedom is 3. Hit enter, paste, and voila, there is our p-value, 0.025 roughly. So we have our p-value is 0.025, so we can come to a conclusion. 0.025 is lower than our alpha of 0.05. So if we have an alpha of 0.05, then we would reject H naught. But if we had an alpha of 0.01, that would be greater. We would fail to reject. Why do I bring that up? Well, some of our answer choices mention a 1% significance level and a 5% significance level. So we have to know when do we reject and fail to reject. 0.05, our p-value is lower than that. Oops, sorry. Let me get my pointer. So 0.05, our p-value is lower than that. We would fail to reject at the 1% level, but it's definitely enough to reject at the 5% level, so our answer is D. Now, there is still a faster way to do this problem using the calculator. So here's a much faster way to do it. First of all, you have to, if you're doing chi-squared goodness of fit, you have to do to list. How do you know that? If you go to stat test and you look for chi-squared goodness of fit, which is way down here, it's going to prompt you for list 1 and list 2. So let me go get out of there. Mode clear is a good way to get out. Hit stat and edit. And I've already entered the list. We have 77 type O, 85 type A, 23 type B, and 15 type AB. And then if we go and check what is our expected values, that's in list 2, 92 for type O, 80 for type A, 20 for type B, and 8 for type AB. So now we're going to go and run the test since we have our list set up. So I have to go from the bottom, it's the easiest, hit enter. So you can see it defaults to list 1 and list 2. My degrees of freedom is off here. I have 4 values in list 1. So that would be 4 minus 1 would be my degrees of freedom. And then I can come down here and hit calculate. And you can see I get the same 0.025. And there's a 9.33 test statistic. And you can also see your contributions. So if you want to see your contributions, the easiest way to do it is to go to stat edit. Now it's not going to show it in the list here. If you scroll through, there's nothing on contributions. So what you can do is you can go up to an empty list and you can say, I want to see the contributions here. So I'm going to hit second list, and there it is, 7. So I'm making list 3 my list of contributions. And you can see here, if we look 2.44, 0.31, 0.45, my 6.125, my biggest contribution is from the last set, which is type AB blood. Number 2, to test the claim that dogs bite more or less depending upon the phase of the moon, a university hospital counts admissions for dog bites and classifies with moon phase. So you can see there are 32 for the new moon, 27 for the first quarter, 47 for the full moon, and 30 for the last quarter. Which of the following is a proper conclusion? So they're talking about the data. Now you see 2 of these with proofs. Those are not correct, all right? We're looking at the distribution of dog bites across the moon phases. And the question is, are they equally distributed or are they not equally distributed? So we're going to perform a Chi-Square GOF test because we have one variable, which is the phase of the moon, and we're recording how many dog bites occur for that. So we can tell, first of all, go ahead and cross off that proves and that prove, and then we're going to go ahead and get to our test. First of all, we should come up with hypotheses. The null hypothesis is that dog bites occur equally during all moon phases. The alternate is that they do not occur equally for each moon phase. So we're going to assume each phase of the moon should have 25% of the dog bites, or 0.25 for each. So we'll have to do some math. We add up the number of dog bites we have, which is 136. If we take a quarter of those, we expect 34 for each moon phase. Now, we're going to conduct a chi-square test for goodness of fit if conditions are met. So random, we have to assume the sample is representative. It kind of just says they recorded the dog bites. And it doesn't say anything about randomness. The whole point of randomness is a representative sample. They didn't say it was representative, so we have to assume it. 10% condition. We will assume that 136 is less than 10% of all dog bites. That probably seems fair. Large counts. All expected counts are 34. That's what we calculated on the previous slide. So that means they are at least 5. We need all of our expected counts to be at least 5. So now we're going to go ahead and do the do part, which is calculating the test statistic. And this is straight off your formula chart. And so for the new moon, we had 32 observed, but we expect 34 for each phase. So 32 minus 34 squared divided by 34. So all of these are going to have a 34 on bottom. Then you're going to be subtracting 34 every time because the expected counts are the same for each phase of the moon. The observed are slightly different. You have 32 there, 27, then 47 and 30. And if you do all the math, you'll get 7. So now we want to calculate the p-value of getting a 7 to infinity with degrees of freedom of 3. All right, so we are now going to go ahead and do chi-squared CDF. So that's second distribution. And it's right there, choice 8. So I'll choose 8. This time, instead of 9.33, which we have for problem 1, we have 7. Our upper is always infinity, so one less thing to remember. And in this particular case, our degrees of freedom are also 3. Remember, we got that because we have 4 categories. We subtract 1. And when we run that, we get a p-value of 0.072. So now we have our p-value, 0.072. And because this is greater than a typical alpha of 0.05, we fail to reject H0. There's not convincing evidence that dog bites do not occur differently across the moon phases. Now we'll do the shortcut video. So 2 things, we got to set up our list. And so we already have a list set up from problem 1. I can actually go up here and hit clear. Enter. So make sure you go to the very top, hit clear, and then enter. I'm going to clear the contributions as well. All right, so our first list is what we observed, 32, 27, 47, and 30. Then the next list is what we expected, all right, our expected counts, which were 34 across the board. So I'll hit 34, 34, 34. Oh, my 4 is not working so well. And 34. There we go. So there are our expected counts. And then once we set up our 2 lists, we can hit stat. We can go to test. And it's Chi-Square GOF, goodness of fit. Again, that's when you just have one categorical variable. You have list 1 and list 2. And again, we have degrees of freedom of 3, so I don't have to change that. How do I know? Because there are 4 outcomes on the categorical variable, new moon, first quarter, full moon, last quarter. So you subtract 1 from that, and that's your degrees of freedom. And you can see here is our test statistics, 7. Our p-value is 0.07. And if I want to see what these contributions are, I can hit stat and then edit, and then just go to a new list. Make sure you go to the top and say, hey, I want that to be contributions, which is 7. Then hit enter. It will recalculate, so it won't remember the old ones. It'll give you the new ones. And you can see that our largest contribution to the chi-squared statistic was the full moon with 4.97. So there you go. So now we know that we have the test statistic. It does not give sufficient evidence to conclude that dog bites are related to moon phases because the p-value is quite high at 0.071. Problem 3. A study of marital status of adults in the United States results in the following segmented bar chart. Which of the following is the greatest? Well, first of all, we're looking at numbers here, numbers, all the above are equal. It's impossible to tell. Well, the segmented bar chart shows percentages, not numbers. It is impossible to get numbers from this type of display. You could have 100 marriages here, or 100 adults here and 200 adults there, and you would never know. So it is impossible to determine the answer without knowing the actual numbers of people involved. Problems 4 through 6. The relationship between winning game proportions when facing the sun and when the sun is on one's back is analyzed for a random sample of 10 professional players. The computer printout for regression is below. For some reason, I get the impression maybe it's tennis. I don't know. So first of all, the coefficient of facing is 0.9203. So that is our slope. You can see they kind of rounded it. They're just doing 0.920. Then we can go ahead and cross these off. Facing is the x. So whatever is right here, that's your x value. Okay, so that eliminates 3 of our choices. And we have, you can see automatically, I guess it's B. But just to continue on, the coefficient of the constant is 0.0559. This is your y-intercept, which is basically 0.056. And our answer is B. Then they ask us, what is the correlation? Well, we know r squared here, right? And we know r squared is 0.986. Well, r, which is correlation, is plus or minus the square root of r squared. The reason I say plus or minus is r squared is always positive, but our slope could be negative. Here, our slope is positive, so we're going to have a positive square root, and we get 0.993. Number 6. For one player, the winning game proportions were 0.55 and 0.59 for facing and back, respectively. What was the associated residual? So residual is actual minus predicted, so we're going to need our predicted back. And we'll go ahead and plug in what facing is, which is 0.55, and calculate our predicted for the back, which is 0.562. Well, the actual for back was 0.59, so we subtract those two, and we get 0.028, which is our residual. Number 7. Data are obtained for a group of college freshmen examining their SAT scores, math plus writing plus critical reading from their senior year of high school, and their GPAs during their first year of college. So the resulting regression equation is predicted GPA equals 0.55 plus 0.00161 times their total SAT with a correlation of 0.632. What percentage of the variation in GPAs can be explained by looking at SAT scores? So we want r squared, which is the coefficient of determination. And all we have to do is square r, and we get 0.399. And we basically move the decimal and change it to percent. The answer is C. What fault do all of these sampling designs have in common? First one, the New York Times plans to make a prediction for the Republican presidential nominee based on a survey of its readers. So I can tell you I read the New York Times, and yes, it has a strong selection bias. This is people who read the Times. It is not very representative of the general population. Then we have, I'm going to show the answer accidentally, it's B. Let's go ahead and go to number 2. An internet site asks viewers to vote on their choice for movie of the year. This is voluntary response bias, a big no-no. Number 3, a stats teacher randomly picks a sample of the students and interviews each one concerning the clarity of the teacher's explanation of new concepts. That sounds like strong response bias there. So if I asked you, how good a teacher am I? You guys are going to tend to be positive because I do your grading. Number 9. Oh, so I should probably reaffirm that yes, all of these designs have errors that lead to strong bias. Number 9, suppose that for a certain coastal city in any given year, the probability of a major hurricane hitting is 0.4. The probability of flooding is 0.3, and the probability of both a major hurricane and flooding is 0.2. What is the probability of flooding given that a major hurricane hits? Well, let's go ahead and write down what we know. Probability of hurricane is 0.4. Probability of flooding is 0.3. Probability of hurricane and flooding is 0.2. We want to know the probability of flooding given a hurricane. So we go to the formula that's on your math chart. And it basically says, okay, you take this one and do an and with it and divide by the probability of the given. So the probability of hurricane and flooding is the same as flooding and hurricane, that's 0.2. The probability of hurricane is 0.4. You divide both of those and you get 0.5. Number 10. A telephone executive instructs an associate to contact 104 customers using their service to obtain their opinions in regard to an idea for a new pricing package. The associate notes the number of customers whose names begin with A and uses a random number table to pick 4 of these names. She then proceeds to use the same procedure for each letter of the alphabet and combines the 4 times 26 samples, basically, and gets 104 results into a group to be contacted. Which of the following is correct? A, her procedure makes use of chance. That is true. Is it a simple random sample? Actually, this is a stratified sample, so that's false. Each customer does not have an equal probability of being included. Z is probably more likely because there are more A's to compete with. D is false because bias is a result of undercoverage, response bias, voluntary response bias, and non-response bias. It is not due to your sampling technique, so D is false. And then E, with this small sample size, it is better to let the surveyor pick representative customers to be surveyed based on as many features as gender, political preference, income level, race, age, and so on, as are the company's data banks. No, we want to use randomization to remove hidden biases. So the correct answer is A. Number 11. PCB contamination of a river by a manufacturer is being measured by amounts of the pollutant found in fish. A company scientist claims that the fish contain only 5 parts per million, but an investigator believes the figure is higher. The investigator captures 6 fish that showed the following amounts of PCB in parts per million: 6.8, 5.6, 5.2, 4.7, 6.3, and 5.4. In performing a hypothesis test where the null is the mean is 5 parts per million, and the alternate is the mean is greater than 5 parts per million, what is the test statistic? So we're going to need the mean and the standard deviation for this sample, so I will show you how to do that. Okay, so we're going to do one of our stats. Let me just go ahead and clear. If you hit stat, well, and hit edit, we can basically put our data in here. Let me go ahead and clear it out. This is from our previous problems. You go up to the very top, hit clear, and then enter. I didn't have to clear them all out, but it's kind of nice. All right, so we're going to type in the data: 6.8, 5.6, 5.2, 4.7, 6.3, 5.4. All right. And we get we can basically hit stat calc, one for our stats, enter. And we have list 1, don't hit a frequency list, and then you hit calculate. And there is your mean right up here. And there's the standard deviation for the sample. Don't confuse it with sigma, which is the standard deviation for the population. So now that we have these values, we can go ahead and use the formula. So we need the formula for a standardized test statistic, which is statistic. In this case, our statistic is the mean value, 5.67. And then our parameter is, or our hypothesized parameter is 5. And then we have to calculate standard error for the statistic, which is slightly different from the standard deviation for the sample. We take that number and we divide it by the square root of our sample size. So we can basically fill this all in. X bar is 5.67, U naught is 5, S is 0.763, and then square root of 6, which is our sample size. So you can see the answer is E, because these denominators, it's really the denominators you can see that don't match, resulting in E. Number 12, which of the following is a true statement? While properly designed experiments can strongly suggest cause and effect relationships, a complete census is the only way of establishing such a relationship. And then the next one's similar. If properly designed, observational studies can establish cause and effect relationships just as strongly as properly designed experiments. False, false, false. You need an experiment to suggest cause and effect. Now, maybe if you have some super fancy observational, you can do what's called a quasi-experiment, but you have to be really good at stats to get away with it. Number C is true. Controlled experiments are often undertaken later to establish cause and effect relationships, first suggested by observational studies. Remember, it's much easier and cheaper to run an observational study than an experiment. So those are frequently done first. D, a useful approach to overcome bias in observational studies is to increase the sample size. Sadly, not true. It helps precision, but it doesn't remove bias. In an experiment, the control group is a self-selected group who choose not to receive a designated treatment. Treatments, including controls, must be randomly assigned. E is false. C is true. 13. Two classes take the same exam. Suppose a certain score is at the 40th percentile for the first class and at the 80th percentile for the second. Which of the following is the most reasonable conclusion? So we're like, how do they compare? Well, if someone's at the 40th percentile, right, that score's at the 40th percentile. That means the bottom 40% scored at or below that amount, which means 60% of the first class scored at or higher than that amount. Now, for the second class, that scores at the 80th percentile. So 80% of the class is at or below that score, which means 20% of the class is at or above this score. So it looks like the students in the second class probably did better. Number 14, suppose x and y are random variables with the expected value for x is 780, the variance for x is 75, and the expected value for y is 430, and the variance for y is 25. Given that x and y are independent, what is the variance of the random variable x minus y? So we're going to look at variance, and remember, we only add variances. We never subtract them, unless you set up your equation and then you have to subtract from both sides. But in this case, we don't have to. We just basically substitute the 75 and the 25. So you get B. Number 15, the probability that a person will show a certain gene-transmitted trait is 0.8 if the father shows the trait, and 0.06 if the father doesn't show the trait. Suppose the children in a certain community come from families in 25% of which the father shows the trait. Given that the child shows the trait, what is the probability that her father shows the trait? So first of all, I'm going to say T is the person has the trait or the child has the trait, and FT is the father has the trait. So we know 25% of the fathers have the trait, so we're going to start there, right? 25% of fathers have the trait. And then that means 75% don't. If the father has a trait, 80% of the kids have the trait, and 20% don't. And then if the father doesn't have the trait, only 6% of the kids have the trait, and the rest don't. So we're trying to figure out, let's go ahead and multiply out the probability of the father having the trait, and the child having the trait. So we have 0.25 times 0.8 is 0.2. Probability of the father not having the trait and the child having the trait is 0.75 times 0.06. We get 0.045. We're trying to find the probability of the father having the trait given the child has a trait. So again, on your formula chart, the way I remember it, it's we do an and on top, and then we just divide by the second one for the probabilities. So the father having the trait and the child having the trait is 0.2. The probability of just having the trait is both of these outcomes. We add them up, and we get 0.816.